In this video, we're going to go over graphs of circles. Just a heads up, in this and the next few videos for this series, the main aim will be to give you an introduction to the simplest forms of these graphs, and we'll also point out different features and terminology associated with them. But we won't be exploring as in-depth all of the different transformations we can apply to them. Those transformations are covered in our videos on parabolas especially, and there's another whole series on general transformations of functions and how they interact with each other. So it's actually left as more or less an exercise for you to apply those ideas to these types of equations. Okay, so let's begin. What is a circle? Well, when trying to draw circles using a compass or something, we stab a center point in our paper, we extend some distance coming from that center point, and we trace out every point that is this fixed pink distance from that central point. And that's a circle, right? Every point a fixed distance away from the center, and we called that distance a radius, of course. So now we chuck this guy inside an xy plane, where naturally we place the origin at the center of our circle, and we can restate that definition as our circle being every point whose distance from the origin is fixed at some constant number r, where r of course stands for that radius. So the question now is, how do we algebraically describe what we just wrote? Well, it's more helpful to think about some random point on the circle here, which we'll call xy, with x, of course, being the horizontal coordinate, the blue bit, and y being the vertical coordinate, the green bit. Okay, so we want to give an algebraic description of what we just wrote. So what we need to do is pin down an algebraic way to think about the pink distance on our picture. But that's not very hard at all, because we can see that the x and y values naturally draw out a right-angled triangle for us, and the distance can be described then using Pythagoras, namely that x squared plus y squared equals r squared relationship. And you can see that the right-angled triangle structure doesn't break as you trace this point all the way around the circle. Well, I kind of lie here, it does break at exactly 4 points, but at those 4 points, the equation is still true, and we'll leave it as, again, an exercise for you to see exactly what we mean by that, okay? So that means this Pythagoras lookalike is exactly the equation of a circle, whose center is at the origin. So for example, if I now tell you the radius of the circle is 3, then the equation of this circle would be x squared plus y squared equals the radius square, which is 3 square, and that of course is 9. Okay, so the only other thing we'll do here is to look at an example where the circle has been shifted. Okay, but before we do that, notice there is no sense in adding or subtracting numbers at the end of the equation to move it around. Okay, and that's because the equation doesn't look like y equals something, or x equals something, so we have no direct control over the x and y values of our points. Rather, all movements of the circle will actually come from changes to the axis, which happen again by x and y changing into other things. So let's see that in action. We have here x minus 5 all square plus y plus 1 all square equals 16. So it's clearly following the form of a circle's equation. Right? X square sort of plus y square sort of equals r square. Only x and y have been changed in some way. So before we mess with the x and y stuff, notice the right hand side is 16. So we have the radius being the square root of 16, because remember it's r squared that lives on the right hand side normally. Okay, and so that's going to be 4. So we'll recap the way to think about the way x and y have transformed. We start by pretending they haven't changed, by taking the more basic x squared plus y squared equals 16, whose center from what we just did before would be at the origin at 0, 0 here. Then the radius is 4, so our circle would look like this. Then x gets changed into x minus 5, and whenever x or y change like that, we imagine the axes moving. So in this case, x minus 5, meaning that they go left by 5. Then y changes into y plus 1, so the axes will move up by 1. So this actually would be a totally correct graph, okay? But again, we normally like to reframe that as how the circle has moved, and how the circle appears to have moved is always in the opposite manner to how the world behind the circle moved, how the axes moved. Okay, so if we reset the axes, we could instead think of the circle, and in this case, really track the center of the circle. That's the easiest way to keep track of it. And that center has gone right by 5. Notice it's the opposite of the -5 direction. And then down by 1. Notice it's the opposite of the +1 direction. So we label that center 5, -1. And we indicate that the radius is 4, and we are done. Now, in terms of what I'd be looking for in your pictures, of course I don't expect you to draw perfect circles, but don't make it too ridiculous. We do want you to respect how big things are meant to be, though, especially in relation to each other. What I mean is the circle is surely big enough to hit the x-axis twice, and that's because the radius is 4, but the center has only shifted down by 1. And likewise, it's expected to completely miss the y-axis because it's moved a whole 5 units to the right, so if the radius is only 4, it won't manage to reach. So we care about stuff like that, so make sure you're aware of how all those numbers in the equation would relate to each other on the graph. Okay, so that's all for this one. Thanks for watching. See you next time.